So today we will talk about sampling and the use of Markov chains for sampling. Okay. So let's start from what is sampling. So don't read anything on the screen. Just think about this question. You have a nice distribution, say, I don't know, Gaussian. Okay. And think about only for now just one variable. I want to sample a number, literally, right? And I would like it to have a Gaussian distribution. How would I code this up on my computer? So it's one thing to be able to write it down mathematically. We know the density of Gaussian is e to the minus x squared over 2. It's another thing to create samples that actually has that distribution. These are two different things. So you would usually assume, so you didn't do anything about it yet, don't worry. So you'll get there. So you'd check first what kind of things I could actually do. Maybe it's reasonable to assume your computer can toss a coin fairly. I don't know. It will pick either 0 or 1 bit randomly. Even this is questionable. Like, are we able to truly simulate a fair random coin or not? Suppose you do that, and maybe you can also roll a dice. Good. What else? Like, usually quite often we are okay to assume I can also sample from an interval. Say from 0 to 1, I could pick one uniformly. It's not clear how are you going to do this, but so this is like the first thing you could think of. Usually maybe you just divide it up into so many little pieces and then you pick one of them randomly. It almost looks like a random number. I don't know. Or maybe you do bisection. You take the interval, you take either first half or second half randomly, and you keep doing that. That's also not. So, okay, suppose we are able to sample uniformly randomly from an interval val on our computer. And then we are able to roll a dice, toss a coin. What can I build up on top of this? Measure, okay. But what do you have in mind when you say measurement? I see. So you can collect statistics. Yes. That's not the direction I was asking about. Yeah, that's a good idea. What I was asking about is like, suppose I have algorithms that creates a uniform sample, that tosses a coin, that rolls a dice. Now you ask me, I need an algorithm for sampling a Gaussian. How would I do that? Okay. So this is, if you never thought about this before, it's a bit strange. I remember when I first started thinking about this, like before I thought about sampling, I thought I knew, right? Because I have the math, but then I realized that math doesn't give you actually a sample on your computer. You just want to make that math kind of algorithmic. All right. So one standard trick, this I took from our textbook. So let me zoom in. It's a little small. So, when there's a lot of equations, it's, I think, good idea to just use the textbook so you see it again, you don't get confused. So here's a theorem that is going to help a lot in this type of questions. The theorem says the following. Suppose this guy is the uniform. Then I take some cumulative probability function. So let me remind you what this was. So if I have some random variable x, if t was probability of that random variable being less than that t. And when you know that cumulative distribution function, you know everything about that random variable. Okay. Now, suppose you got such a function, and what you would like to do is this. You will sample a number uniformly between 0 and 1. And you're going to put that number here. And you will take the inverse of this guy on that number. Okay. It's a little strange looking. And it says this actually reproduces that cumulative distribution function. Why? Well, I sampled a number u uniformly. And I'm looking at f inverse u being less than some number. This is the same thing as u being less than that. And probability of a uniform guy being less than a number. What is this probability? Probability of a uniform number between 0 and 1 being less than half. That's half. So whatever number you get here, that will be that probability. And this little trick means you're able to reproduce your F, okay? So the only reason this thing worked out is this U is uniform. Because U uniform less than any threshold is equal to that threshold. Okay, well, then what does that mean? Well, that means as long as you can compute this quickly, you have hope of sampling from the distribution corresponding to this one. So let's make an example. Suppose I would like to sample from exponentials, random variable. Its probability density is like this. So this just means positive x, so don't worry about it. And this is the cumulative distribution function of this random variable. And let's execute this idea on this random variable. So the inverse, apparently you can just take logs here and look at it. So the inverse of this function turns out to be logarithm 1 minus p, blah, blah, this one. So basically, this is your function going from x to a number. Try to compute the inverse. Okay, this is how it comes about. Now, I do know the inverse explicitly. All I need to do, pick a p uniformly random between 0 and 1, plug it in, get the answer. That answer will be literally sampling uniformly from exponential random variables. Okay, so that's like how you start off. And there is a little more clever trick to build a Gaussian of uniform. It's called Box-Muller method. I'll give you a 2D version of it as an exercise. It's a nice thing to go through, but we already use that stuff implemented. So any library you're using will have a Gaussian sampler. This now you're thinking about what kind of algorithms are under the hood when I call a sampler. Okay. Now, all right. So these are the type of stuff that we kind of mathematically are able to write down, like exponential. I know the formula. Gaussian. I know the formula. Right. It usually doesn't end there. So as Tien was saying, like I got some application. I want to create a sample on the type of data I'm dealing with in my application. It's not like some Gaussian sampling or exponential. I want a sample that represents my problem, right? So then how do I do that? There are many ideas, and there's always a new idea. It's not a settled discussion. So one common thing is called rejection sampling. So let me first tell you the idea, then I will show you this figure and do the math more precisely. So usually you don't even have like a probability distribution. You have something like a big distribution, but the probability of the entire space is not 1, it's like 110 or something. You have to normalize. Usually this is what you see in applications. You have like, suppose you had some data and you measured probabilities, with probabilities such as, with say 10% of my data is looking like this, 5% looking like that. That's usually what you get in applications. You don't have like a nice probability distribution to work with, okay? So then what you would do, you will do some normalization, and then you will turn it into a probability distribution, and theoretically that's your target. Now, we don't know how to sample from it. That's just what we want to do. So now what you need to do for this rejection sampling idea, find something that you know how to sample from, okay? Multiply it with the numbers so that at every point x, the density here is bigger than the density of your target. Okay. And then after that, what do? You first sample from this. You need to come up with something that gives you an upper bound and easy to compute. This is what you will use for this rejection sampling, okay? And then what you will do, sample from that easy thing. Now you get some sample x naught. Plug that in to this density. Now it gives you a number. The density at that thing you sampled is blah. Multiply it with the c you had. Now you have an interval from 0 to c times x naught inside the density q. Sample uniformly from this interval, okay? And now you get a number. Okay, I'll tell you why this makes any sense at all. Okay, I'm just describing the steps now. So I sampled from easy distribution. I sampled uniformly from this interval. And after that, what I do, I take my sample, I plug it into this density. Okay, so you need to have an estimate for the density. You're not able to sample from it. You need to have an approximation to this number. And you check if this density is bigger than the threshold I cooked up. I reject it. If it is less than, I accept. Okay, that's what's called rejection sampling. And you will see this actually works out. Okay, this looks very funky, but it's mathematically legit. So let's just look at the figures to have a schematic, picture on top of our head. So you are trying to sample from target distribution Px, and you are able to create samples from this guy Qx, which is an upper bound. So what do? You sample, and then you're going to plug that into your density Px, and you're going to check where this is accepted, where this is rejected. It's like, roughly speaking, how it is going to go. Like you sample, there's like a threshold of rejection. Below that, you're okay, about that cutoff. Okay? That's how it is going to look usually. And let's see. So for example, the second one turns out to be, they are trying to sample from gamma distribution. Don't worry what that is if you don't know. It's just one distribution statisticians use all the time. You might see it in your applications too, but it's not terribly easy to sample from it. So this is their blue. That's what they want to do. This is the target density. And then the bigger guy is easy blanket. Okay, upper bound, think about it like a blanket. It's always above, but it's easy to sample. So you sample from that, then you do the uniform thing. And uniform thing is trying to catch the correct cutoff. Yeah. So that's the pictorially how it looks. And if this is your first time seeing this might look very weird. So let me show you this actually is mathematically legitimate. Okay. And this again, since there's a lot of equations, I did not write it by hand, not to confuse you. I took it from the textbook. So suppose I sampled this X naught. What's the probability of acceptance? So until Px naught, if I sample any uniform number from 0 to there, I'll get accepted. Because I sample a number, I check if I'm below, accept, above, no. Okay. All right, very good. So, and then you compute through that. This is the probability you get for acceptance. Now, how about I first need to sample this guy, right? Then check if it is accepted or not. How about first proposing, then accepting? You compute it, you put the definitions in. This is what comes out. So this is the probability or the density as attached to proposing this sample and accepting, okay? Now you integrate it through, and what do you get? Probability of acceptance for any sample you could come up with. So there are like lots of different samples you could come up with. They all have a density attached to them. It's like probability of sampling that thing with respect to Q, right? But that for every single one of them, acceptance probability is determined with this uniform threshold, whatnot. So you look through all samples and you look through probability of accepting in any of them, okay? And then that gets you here. And then eventually you say, okay, now if I look at like a posteriori, if I have a sample that is accepted, what's the probability of that sample being a particular number X naught? Okay, and you compute it, it exactly comes out as what you want it to be. It comes out as your target density. So it's all like kind of black magic. So you cook the definitions up so that at the end you get what you want, and what you want is this equality. When something is accepted, density of that being a number should be equal to your target density. Okay? But the point is, we are not able to sample from this target density P. We are able to sample from this Q, and which does the trick for us. Okay. Yes. Questions? Very good question. So how do you decide for Q? That's not an easy question. Okay. So the more similar your Q is to your target P is the better, of course. You have an idea about P, but you don't know how to sample from it. Okay. So you collected measurements about P. You have an idea about how your data is looking like. You have estimates for density and whatnot, but you're not able to create a sample similar to your data. You want to simulate, basically. Think about sampling as simulation. Yeah. So you have an idea about P, but you're not able to create something that looks like that P. Okay. So then you need to find out a Q that is a blanket for your P. So what is Q? Q needs to satisfy only this property right here. At every data point, the density that you target should be bounded from up with the Q you're able to sample times a number. And the answer to your question, there is not like a common recipe that I can tell you, do this, do that, that will solve all your problems. It's usually problem specific. You try to come up with a Q depending on your problem structure. And that's kind of an art more than a science. It comes off of experience with dealing with a lot of problems. Okay. There are some algorithmic approaches, but not so strong. So that is rejection sampling. And now another thing, rejection sampling is a good idea, but as the dimensions get higher, it starts getting hard to execute. The reason for that is what were we doing? We are sampling with respect to Q. Then we are sampling a uniform number for an acceptance threshold. And if it is below accept, above reject. When you go to high dimensions, your rejection probability starts increasing. You have say 100 coordinates. One of them gets rejected, you're rejected. So the issue of rejection gets harder and harder as coordinates gets bigger. In a way, curse of dimensionality is more about if you're trying to compute with something that is already high dimensional, no matter what you do, you will have to throw at a lot of computational resources. That's what they mean with curse of dimensionality. Another way to think about curse of dimensionality is you have a problem. Here I'm talking about, say, just one random variable. Suppose I ask the same question with 100 random variables. How does the complexity of problem scale? So if it is scaling linearly with dimension, that's usually fine. But if it is scaling faster with dimension, then they will start calling curse of dimensionality. Dimensionality is sometimes a curse, sometimes a blessing. Sometimes it's useful. Okay, so this rejection sampling, it's hard to scale this up, basically. That's what I was trying to say. Something you would see more commonly done in higher dimensions is something called importance sampling. So you have a function in mind and you're trying to estimate its expectation with respect to some probability modeling your situation. This is your function, this is that probability, this is the expectation. And we have no idea how to sample from this guy. So what do? You create something you could sample from. Q here. Okay. And then Q, you're able to sample from it. And here in this setup, we are assuming we are able to estimate pi x, okay? Even though I'm not able to sample from this distribution, when somebody gives me a data point, I'm able to estimate the density at that data point. That's what we need to assume, okay? And this density estimation, you could also think about it algorithmically. There is a whole bunch of density estimators implemented that you can use all the time. I don't know. So for example, anybody did any clustering type work recently? No? If you do say, for example, clustering, a lot of clustering algorithms already calls density estimators without telling you. So these are already implemented, pretty good implementations. So if you have good enough data, I would say don't be scared about this part. Okay. All right. Now what you do, you just do this trick. You correct. You think about importance of the number you sampled. If this is big, it's good shot. You got an important thing there. If this was very small, it's not so important as a sample. That's why it's called importance sampling. And then what you do, you sample with respect to your Q. You sample a whole bunch of points. At every single point, you do that correction, and you evaluate your function, you sum it up, you average over, and that's an approximation to your expectation. Okay, this is called imported sampling, and this is done in higher dimensions much more often than the rejection sampling. And there are a lot of tricks around this. Again, the same question applies. How do I pick the Q that will make my life easy? As I said, it's mostly an art. There are some algorithmic approaches, but there's not like a thing that I could give you and say, just call this library. So that's more or less the main basic ideas in sampling. Now I would like to talk about the Monte Carlo method based off of sampling. Any questions so far? And as I said, it's not a settled discussion. I think there is a big conference only on sampling theory every year. You know, so there's like, what are the big conferences in machine learning? NeurIPS, ICLR, blah, blah, blah. And there's another conference as old as NeurIPS. I think it's called like sampling theory and applications, like a whole bunch of people come up with new algorithms to sample better every year. Okay. Now, one reason that we care about sampling is usually to estimate expectation of a quantity I'm trying to understand. Okay? And if you're able to sample, suppose you come up with a scheme to sample from the probability distribution that is modeling your data in using one of the tricks we mentioned or something else, okay? Then you can use this to approximate this expectation as follows. Just sample those points, you know, put your density on them, multiply with your function, sum it up. If this was uniform, this will be 1 over the number of data points. You'll get literally sum up and divide averaging over. If this is a different distribution, this is not how it is going to look like. Okay, how good is this? So you're now trying to think about what I created by this approach. Mine difference from the actual true expectation I cared about. I don't know if you remember or not, we had an inequality called Chebyshev's inequality when we were starting very early on in semester basics of probability. That's one of the first things probably we talked about. That says this difference being bigger than a threshold t is less than equal to variance of the thing divided by that t. But by definition, when you have 1 over n, that shows up in that Chebyshev inequality, and we have done this. I guess you guys had an exercise called law of large numbers, doing almost exactly the same. But the punchline is, after you do that probabilistic stuff, you end up getting basically an estimate. And let me just stop here. You end up getting an estimate that scales with 1 over root of the number of samples. So the rule of thumb here is, if you're using n samples, you can think what you created as a variance bounded by a big bound divided by square root of that n. Okay, that's how it's scaled. But it's not too bad. It's not great either. It's not like it's scaling n squared n to the 5th. It's scaling root n, but not too bad. Another good thing about this Monte Carlo is it doesn't see the dimension at all. You get the same exact bound, whatever dimension you're working on. It only sees the sample size. Okay? That's why it's kind of easier to scale up. Okay, this is standard Monte Carlo. Now, the issue here is that, let's say you're, depending on how your function behaves, sampling may or may not work so well. What do I mean by that? Your function could be something very bumpy, or it could be something kind of smooth, you know? And you're trying to sample from a domain and trying to estimate what your function is doing. Think about what you sampled is like kind of pinning it down. You say, I sampled here my function is doing blah. I sampled here, it's doing blah. And off of those samples, you're trying to estimate on average what it is doing. But if your function is super bumpy, going up and down a lot, then this could kind of fail miserably. Okay. And where do you see it in the bounds? Look at the bounds once again. You see the variance of your function divided by root of your number of samples. If this variance was already huge, then you might need heck a lot of samples. Okay. So what do you do in that case? So if your function is not so nice, it's jumping over all the place, variance is high, then people start talking about variance reduction techniques. There's a ton of things about it. One thing that has a very good implementation is an idea called Hamiltonian Monte Carlo, and that's what I'm going to tell you. And after that, I plan to move on to Markov chains. Okay. So so far so good. Do you guys understand the issue? Like Monte Carlo, good, works in any dimension. How about the errors? Depends on the variance of your function that you're trying to estimate divided by root of the number of samples. Okay, so what do I do if my variance was big? So here's something that is inspired by physics. So I need to teach you a tiny bit of physics, unfortunately. Okay, and this thing is useful for so many problems, this physical idea that I'll tell you about. So it's not a waste of your time. It's not only useful for sampling and Monte Carlo, it's useful for many other things. Okay, so if you think about some stuff moving around, probably somebody told you there's like kinetic energy, potential energy, right? You remember those days in high school or college or wherever you learned about it. And then there is this preservation of energy idea, right? So the summation of potential and kinetic should remain constant. The total energy is called Hamiltonian. Okay, this thing on the left, it depends on where your particle is, position, and momentum. In our computer science world, position literally is the thing that encodes the state of your whatever you're dealing with. It's just a vector that encodes the state. Okay, and momentum is in which direction it's changing. That's basically what it is for us. Okay, so what is momentum? In physics terms, velocity times mass. What is velocity? In which direction the thing is moving. Okay, so this is about the change direction. This is about where I'm at. This is where my sample is. This is where I want it to go. Okay, and then you'll usually have some potential energy and kinetic energy. So for us, usually potential energy is given by logarithm of the density or something. And the kinetic, you kind of get to cook it up. Okay. All right. Then to preserve the energy, there is particular equations the change has to obey. So the change in kinetic energy in terms of velocity is equal to the change in my location with respect to time. This is like equations of motion. Okay, so this is a more general way than if you saw Newton's laws, for example, you can derive them from here. You might be thinking what this has to do at all with my data science. We'll get there soon. Bear with me a minute or two. Okay, so now the point here is like, since there are equations describing explicitly the relationship between the changes, as long as you update one of them, you know the update for the other one. That's what we care about. Okay, we are going to keep updating our sample. And the way we update is going to come out through these relationships. And our textbook even works out why the energy is conserved to have fun. We don't need to worry about it. So the idea here is like, I'm going to start a sample, and I'm going to try to imitate as if I was through a physical system. And what you do is like, you want to sample from places where density is high. Okay, and if you put the potential energy as minus your density, okay, you end up looking at places where like potential energy is small if you design it that way. Okay, but usually what you would like to design is like, you want to sample from where potential energy is high, kinetic is small, so it's like a particle in stable situation. Okay, all right, so all right, then what do you do? This leapfrog integrator, what they call, funny name. It's not integrating, it's also not a frog, but that's what it's called. So it's basically keeping track of the changes according to equations. Basically, this is already implemented. You don't need to worry about it. As long as you start your change, the implementation takes care of the correct updates according to rules of physics. Okay, and After all this, what do? You start just generate some random momentum. Okay? And you're at a certain random sample you created by some arbitrary way. Now, the idea is like try to direct the sample in a way where density is high. I don't want to sample from places that has nothing to do with my problem. But if I'm just sampling all over the place, that might be what I'm doing. If my function has, say, bumping too much, I want to sample the places where it bumps. Okay. But the previous sampling idea, you are sampling all over the place. It has no idea about your function at all. So here what you do, this is your change in the kinetic energy. You update your momentum, you run this leapfrog, whatnot, and then you update your location, and you say, okay, after I run this couple of iterations, this is the proposal for my next point for sampling and for momentum. Then how do you know if this is a good idea or not? Well, if you're able to imitate this physical thing, energy should be conserved. That means the Hamiltonian in your proposed place versus what it was should be close to zero. Okay? And you put that in as an acceptance or rejections probability. Okay, you just look minimum of one, blah, this, and you say, I take this as a yes for my next sample with probability alpha. For example, if this was exactly zero, with probability one, you say yes. Okay, but if you change the energy a little bit, there's always error in computations, but not so much. It will still be highly likely accepted. And at the end, what you're trying to do, you're trying to make your computer go through the trajectory where energy is preserved and your function is kind of highly efficient. Okay, so that's the Hamiltonian Monte Carlo. This is the idea behind. You don't need to learn all the technical details. It's implemented very well. For example, there is this thing called blackjacks in JAX of Google. It does this very quickly, but it's not the only one. So if you just Google Hamiltonian Monte Carlo, there will be a whole bunch of libraries popping up. You can pick the one that is closer to what you're used to. If you're a PyTorch person, TensorFlow person, whatever. Okay. The only thing that you need to think about here is like, how do you cook up the Hamiltonian? And the rest will be already implemented. All right. So that's Hamiltonian Monte Carlo. If some of the technical details went above your head, that's fine. I'm just trying to make sure you know this thing exists. And if your Monte Carlo is not working out, go for Hamiltonian Monte Carlo. The usual Monte Carlo, people in the field usually calls it vanilla Monte Carlo. It's just too simple to work all the time. Okay. This does work for a lot of problems as well. Okay. Now, as you have seen, the main issue is creating healthy samples. As soon as you have that, you can run your Monte Carlo, Hamiltonian Monte Carlo, whatever. Okay. Now, how do I create healthy samples? We talked about rejection sampling and importance sampling, but that doesn't solve all your problems that you deal with. For this, we will use Markov chains. So another common applications of sampling is what's called data augmentation. You know, you got some data, there's gaps in your data, and you need to fill them before developing a model. What can you do? One thing you could do is like you can try to sample from your data and put that in to your fill in the blanks type of filling gaps. Okay. So for example, I have some friends working on places like Zillow or whatnot. They tell me that's what they do all the time. You know, there are data about houses in a neighborhood, but then it's not fully complete. They either don't have all the aspects of the house data they want, or they do have data very well in this neighborhood, next one, not so much. But they want to still guess about the city, you know. So what they do, they just data augmentation. Create samples that fills in that gaps and then build model afterwards. Okay. So many ways to motivate sampling. Now, It's not easy to pull though, it's not easy to sample. And using Markov chains is a general and quite efficient idea. So what's a Markov chain? A Markov chain is the same thing as taking a random walk, okay? So let me start from the random walk. Suppose I have a graph and I'm starting a random walk at, say, this node 1. And then there are probabilities attached. Here I could either go to 5 or 2, okay? Since these are probabilities, the summation of them should be 1. And let's say 1/3 here, 2/3 here. You take one of them with the probability attached. Again, you keep doing that. And suppose you take a long random walk. Suppose you did like 100 steps this way, okay? And now you're at a very random situation. And ask the question like, what is the probability of at the 100th step you are at second node? What's the probability of at the 5th node? At the end of the day, you will give me an answer with 5 coordinates, which tells me your estimates on the probabilities of being in some of those nodes. Literally what happens is like, at the beginning, I was here. So my vector representing the probabilities at the beginning was literally just 1, 0, 0, 0. Right? There are 5 possibilities, 5 nodes, and I know I am at the first one. So it's probability 1. Now you take a second step. Well, you know, with probability this, you're at 2. With probability that, you're at 5. So let me write down the second step. So now your second step in the random walk, the probability vector will look like this, right? With probability 1, 2, you're at 2. With probability 1, 5, you're at 5. And now you'll keep doing this. So the point is like, you feel like after you do this enough, this random walk already gives you kind of a reasonable sample of this network. Like it kind of gives you, after I did this say 100 times, and the vector right here after 100 steps should give you an idea of what typically happens in this network. That's kind of the intuition, okay? Now we will formalize this, but this Markov chain and the formal stuff you're about to see is just this intuition, okay? You're just taking a random walk, and the randomness is determined by how connected are the edges. And after some point, you're trying to estimate how does it look now. Okay, now Markov chains was invented by statisticians much before computer science was even a field, probably. And it's exactly the same thing as what a computer scientist would do if you're taking a random walk on a graph. Okay. So here is how Markov chain formalism goes. You have n states. Think about them as n nodes in your network. And then there is a transition matrix. What does that mean? These probabilities are the probabilities determining going from, say, 1 to 1, 2 to 1, n to 1. Okay. These are like the weights of those edges. And at step T, P1, T, P2, T, Pn, T, these are the probability estimates on being in some of those states. Okay. Okay. And how does the update go? You take wherever you were at step T, you multiply it from right with the transition matrix that records all the transition probabilities. Now you're at your step T plus 1. So basically, every time step is just multiplying your vector with the exact same matrix. You keep multiplying with that matrix. Okay. All right. Now the question is like, is this eventually going to get stabilized? You know, say I did 100 steps, I'm doing 101. Am I going to see a very similar probability vector or like maybe even the same? Okay. When it stabilizes, it's called stationary distribution. That's equivalent to kind of uniformly sampling from this network. Okay. And the way we will use Markov chains to do sampling is like your target distribution that you want to sample from, which is not easy to compute with, will be when this thing converges and stabilizes. The target distribution will be the stationary distribution. And we will design a Markov chain, which will be easy to compute with. And you let your computer do some random walk. After some number of steps, just pull a sample, and that will hopefully give you a good sample of the target you are trying to work with. That's the main idea in this. Let me now flesh this out in more details. Okay, this is how the update goes. And I was here just doing, say, one multiplication. For example, I am in here. I'm going to multiply it with the matrix. Let's just look at maybe the first coordinate to understand. This vector is multiplied with the first column. And this is the type of equation you get. And this determines the first coordinate of your next probability vector. And if you do it with the second column, second coordinate, etc. That's how it goes. All right, very good. Now, first question is like, when does this thing actually converge? In some situations, it actually never goes to anything stationary. It just keeps randomly walking, gets lost. And there has been a lot of theory in statistics and math trying to understand it. I'm not going to tell you all that theory. I'm just going to tell you one piece, which is what we are going to use. Okay. So the main punchline is this. If your thing is strongly connected, then you expect eventually this random walk will converge. So what does strongly connected mean? A graph is strongly connected. If you pick any node and another one, then you could find a path in between. Okay, so it's like a directed graph. You give me a place and another place, I could always go from there to there. Then we call it strongly connected. Okay, so strongly connected graph is the same thing as what you would hear as connected Markov chain. And if your Markov chain is connected, this idea works out. If it is not, you don't know. Okay, so for example, a way to kind of diagnose that your Markov chain may not be converging anywhere is this. Let's say my random walk visited a state, say state 5. And now it's visiting state 10. It's moving around, right? Now you think, is there any probability that this guy will come back to state 5 or not? Okay. If there is no chance of it, probably there is not going to be any convergence. Eventually, when it converges, there should be a chance of going there. So that's one way to check it out. So they say if you arrive to a state and you will come back to there eventually, for sure, with probability 1, this doesn't talk about when you're going to come back, but just like the probability of that happening. If that's going to happen for sure, then we call it persistent. And if your thing is not persistent, there is no hope already. Okay, it has to be persistent. If it is persistent, are you done or not? Not always, but it's pretty close to this connected idea. Let me just illustrate. Suppose this is my Markov chain or graph. Let's try to see what states could be persistent, what cannot. If I'm here, I could go like this and come back. But if I just get out, if I'm here and don't go this way, go that way, looks like I'm never going to come back. So this guy right here is not persistent. You're out, you never come back there. So just because of this, you don't expect this thing to have very nice convergence properties. But maybe you say, I don't care about this one actually. If I'm converging in some of the rest, that's what I care about. That might be the case. Usually not, but maybe. Let's entertain the possibility and let's look at what else is persistent. Like I'm here. Looks like these guys are not persistent also, but these two look persistent. When you arrive here, well, let's keep circling back. So if you do a lot of steps, you might be just circling here back and forth. Right? Maybe you forget about everything else in this network. That can happen with a very positive probability. As long as you arrive here, that's what you're going to end up doing. Okay, so basically the structure of your network is very crucial on determining if this random walk idea is going to work out for you or not. Okay, now let's define the stationary distribution more properly. Stationary is literally, I am at a probability vector. I multiply it with my transition matrix, nothing changes. That's when it is converged, when it is stationary, okay? This is the definition of stationary distribution. Now, the question is, is there only one stationary distribution? Are there many of them? So here is the theorem about this. This is the only theorem I will show you today. As I said, there's so many results about this, but we don't need those. If your Markov chain is connected, there is a unique stationary distribution. And we also have a way to get there. Okay. So the way to get there is start your random walk. But after you take t steps, take average of all the probability vectors you have seen so far. It's hard to prove this thing will converge itself to where you want, but turns out its average converges there right away. Okay, so you take a lot of steps, then you average over, and this gives you a good approximation for the stationary distribution. And you can actually sit down and prove, if you would keep doing this, you will arrive to the stationary distribution. Okay, and the proof is not so hard. So I don't really care so much about giving you proofs, but I will try to give you stuff that gives also insight on what's going on. How does this look? You say, this is my probability transition matrix. Let me take minus identity out of it. And then, since probability transition matrix has certain constraints on it, like when I'm coming from a state to another one, if I take all the options, they should sum up to one, right? But if I'm coming to a state from a lot of states, so the rows and columns, they sum up to one. Or let me think. I think the rows sum up to one for sure. Rows correspond to going from a state to all other places. Yeah. Okay. So since all rows sum up to one, this cannot be full rank. They have, something in common. What does that mean? Take the row, dot product with 1, 1, 1, 1, 1, 1. That's equivalent to summing them up. You always get 1. Okay. And that's kind of the only thing about this. There is no other restriction. Okay. So when you add that 1, 1, 1, 1 stuff next to it, you get a new matrix. You can give it any name. I call it Bob, B. And this new guy becomes a nicely ranked thing. Okay. So I had n states. So here I got an n by n matrix, and here I got an n by 1 matrix. So in total, I have n to n plus 1. And what I'm trying to understand is, like, if I arrive to a place where it is stationary, I multiplied with p, I get it back. And this is the same thing as saying, put this to the left-hand side. I arrive to a place where p minus identity multiplied gives me 0. So this place is in the kernel space of this guy. Okay. And the kernel space actually has only one vector anyway. It's just one dimensional. So if you have this, you're done. And how do you know you're going to have this? What do? You say, I take that average vector, I multiply it with my transition, and I check the difference with my average vector and see how does that look. You just write down the equation, and you end up realizing it looks like this. The difference is number of steps dividing the difference between two vectors. And those two vectors are probability vectors. The difference cannot be huge. Their coordinates sum up to 1. So that means if you took a decent number of steps, this error will be very small. So eventually you converge there. And the reason I showed you this also gives you a direct way to actually know the stationary distribution. It goes like this. Let's remember our Bob. So if you work through this, when you're at the stationary, that thing times Bob gives you like 0, 0, 0, 1. Okay, because Bob was what? It's this minus this. That is just 0. And P with 1, 1, 1 always gives you 1. Okay, so this is what you're going to get. And this thing is n times n plus 1. It's not invertible, but almost invertible. This has rank n. So you can compute this thing called pseudo-inverse, multiplied from right. And when you know that pseudo-inverse, just multiply it with 0, 0, 0, 1. You get immediately your stationary distribution. Okay. So in many problems, you will be able to figure out stationary distribution without computing anything. It will be evident from the problem. Let's say if it is uniform, then it's going to be 1 over n, 1 over n, 1 over n. But if it is not, this proof also gives you a way to directly compute your stationary. Okay. Okay. Very good. But the point is not not only just knowing this, the point is when I start my random walk, I know also it's going to converge to here when I take the average. Okay. So let me summarize. As long as your Markov chain is connected and you start your random walk, do T steps and take average of them. This is our AT. This AT will get to the stationary distribution you care about. That means after you take a decent number of steps, just take a sample from your random walk. This will give you a good sample for your other purposes. Okay. All right. Now, people want to make this a little more precise. So let's see what I would like to tell you. Okay, very good. So just two little facts before I tell you a little more. To check if you're at stationary, sometimes this lemma is very helpful. If you're at stationary, you can do the algebra and figure out ith coordinate times probability of going from I to j should be equal to jth coordinate times probability of going from j to I. Why? Because if you're stationary, taking one more step does not change anything. Okay? So this you can work out. That's one way to check. And another thing is like at stationary, you have the coordinate of stationary equivalent to a number that is 1 over hi. It's going to be an integer. And what's that integer? Let me take back. Does it have to be an integer? Okay, let me take that back. So that thing will be literally, you are at the stop I, and how many steps you will have to take to come back to that I. The expectation for that is, say, 10. Then in the 10th ith coordinate, you will see 1 over 10. Okay. So there's a lot of structure in the story. And now let me show you what we would do with this. Okay. So far, so good. So I have a connected Markov chain. I start my random walk. I do the average of my probability vectors. And I know that average is looking like the stationary I care about. Very good. Now, what do I do with this sample? I'll use it for Monte Carlo, which means I'm trying to approximate behavior of a function. And that's what's called MCMC, Markov chain Monte Carlo. Use Markov chain for sampling, then use the Monte Carlo to approximate your function. So MCMC is actually double approximation. Your Markov chain is approximating a good sample. And on top of a good sample, you're approximating expectation. So it's twice approximating. Okay? Okay. All right. So how does this gonna go? You sample from your random walk, first step, second step, blah, blah, blah. And then you take the average. You plug that stuff in your function. And you're thinking, this is a good approximation for my expectation. And you do the math, and you have a very clear bound on the error. Okay. So the bound comes out like this. If you just do your random walk, do your average of vectors, and then plug them in, and then compute an expectation that way. This is what this is. What this is. And this is the truth. Pi is my target distribution. This is like true expectation. The error comes out as follows. Maximum number that your function takes when it's evaluated. Your function is like bounded. It goes between, say, 100 and 200. Okay. So then this will be 200. Maximum number times the stationary distribution minus where you're at in your Markov chain. Take that as a vector, sum up the absolute values of coordinates. That's the bound you get. Okay, that means this vector gets closer to this, your bound gets close to 0. Okay? And now people start asking, okay, as soon as this is small, say, as soon as this is epsilon, I'm good. But in which time step t I am at that epsilon? That becomes the crucial question. Like, you'll start your simulation on your random walk. When should you be trusting this thing to give you a good sample? Okay. So that's called a time t where this error is less than epsilon. Is called an epsilon mixing time. When people talk about mixing time of Markov chains, that's what they mean. There is usually some agreed upon epsilon that is small enough, and they would only say mixing time. That means I start my random walk. After how many time steps, I'm confident what I'm producing from this random walk is close enough to stationary distribution. Okay? And there is a lot of work on this. I'm just going to tell you some stuff quick. If I would try to do this full justice, it would take, I don't know how many lectures. Okay. So people worked hard on this, because this is the main mathematical question you need to answer. As soon as you have a good answer to this, just start your simulation on your computer, just let it randomly walk. And when the t is good enough from whatever math you did, stop it, sample. Okay. So 2 resources, if anybody is curious, there's a book called Nature of Computation. It's a fun book. It is very thick, but the point is it's like a storytelling book. You can only, if you're interested, there's a chapter about this stuff. Just go read that part. It's by Chris Moore and Mertens, I forgot his name. And there's another book, Information Physics and Computation by Mezzart and Montanari. And the ideas in this book, some of them was celebrated by a Nobel Physics Prize, not the last one, the one before. Last Nobel Physics Prize is given to AI people. Jeff Hinton, when physicists were getting their Nobel Prize, that this was the last subject of the last one. All right, so okay, now what did they come up with? So the funny thing is, like, the thing they come up with has intuitive roots in literally like electrical networks. I don't know about you. When I was a kid, I used to play with electrical networks all the time and get that 200 volts on my body. Luckily, I never died, as you can tell. So, but the point is, like, you got these things, and then in between there's wires, there's resistance, or it's conductive, whatnot, right? So it turns out, to understand mixing time of Markov chains, you look at that weights, edges, as if they're conducting or not. If it is like very conducive, that means your thing keeps traveling very quickly. Okay, that's the intuition people came up with, and this is how it looks. These are your states or your nodes in your network. Pick any subset you like. Okay, and then the summation of stationary probabilities there is like how conducive is that subset for the moment. Think about it that way. And then, okay, as I said, this is a long story. I'm just going to show you a glimpse and move on, okay? If I don't show you anything, it would be not good. But if I show you the whole thing, it wouldn't be good either. Okay, so I'll just give you a little pinch and we'll move on. Okay, then they come up with another notion of conductance of a set, which is this. You get to pick any other set in your node collection. And as long as your network doesn't have self loops, the set should be disjoint. If there is self loop, you can have overlap. Then what do? You look at your probabilities and the probabilities of going from set S to set T, traveling between these two sets. This is what you're looking at, okay? And you divide it by probability weights of these sets independently. So you look at, so this is like, what is the probability of locate being in this set at all? And then you pick two sets, S and T. You look at those probabilities, pick the minimum one, and on top, look at the transition probability between these two sets, okay? And then this is a notion that should come out, okay, so there is a typo here. Yeah, so there is a typo, but it is easy to fix. So this, of course, depends on two sets now. And then to get it only with one set, you take minimum over all the T you could come up with. And then now you have a number attached to every set. You pick the minimum among all these numbers. And the number you come up with at the very end is like conductance of your entire network. Okay. And if you still are alive and did all this work, then you get a guarantee, mathematical clean guarantee. As long as you know that conductance number, you know how many steps you need to take to be epsilon close to what you want to be. Okay. So that's like a main idea of what these experts come up with. Conductance somehow captures mixing time, but the technical details of this gets quite sophisticated. Let me just do an example and move on. So suppose this is our network. I have n nodes, and all the edges are probability half. Everybody's got two edges, half. And if you're at the boundary, half here, half self loop. Very simple network. Okay. So now try to come up with a set which has very bad conductance. Like it should be big, but there should be very little probability of getting out of it. Like what can you do? Let's say if I take like all the stuff here, then getting out will be just this small probability. That is fine. But then I'll probably miss out from this minimum dividing term because what I left out as t is just one node. Well, this will be small, so I'll get big. So I need to balance going big or small. But before we do anything, let's say you started your random walk here and you waited enough. Then what's the stationary distribution? Well, of course, it's going to be uniform from one of those nodes right there. Okay, so the stationary will be like 1 over n, 1 over n, 1 over n. That I know. Okay. Let me at least put that there. So I know like in the stationary case, it's going to be like pi 1 is 1 over n, pi 2, 1 over n. And if I do what I just said, like if I pick everything except the last one, I'll get this 1 over n, and it will show up right here. And it will flip. It will become an n, right? And it will become an n. And on top, I also have another number, whatever that is. May or may not be a good idea. I played with this. Probably it's good for you to play also. I might put this as an exercise. Turns out like cutting it to half is like a good idea. Like you create two equal sets. There's only one edge connecting them. Okay. And from there, you get something like that conductance being, let me try to remember, like 1 over n, something like that. And then here you get an estimate like n squared log n, roughly speaking. Okay. So on this particular network, you need to wait quadratic time steps, roughly speaking, to get a good sample, turns out. And all you need to do is extremely simple. Start your random walk from here. Let it run. If you have 1,000 nodes, 1,000 squared, it's kind of a big number. What is it? Million already? That means you need to be, if you want to be really sure, wait 1,000,000 steps. Then you will have a very good sample. Okay. Of course, these estimates are very conservative because they are trying to give you full guarantees. So you know for sure if you wait until this theorem much, you're there. But usually we don't wait that much. It gives an idea of how what is the scale. Okay, so that's Markov chains and when they converge. Now the question is like, how do I design Markov chains that gives me a sample from my target distribution? I have a target. I'm going to create a Markov chain just to sample from that target. How do I do that? There's a very general idea called Metropolis-Hastings algorithm. These are the last names of two people invented this particular idea. Okay. So you want to sample from a target distribution, which is right here. And you have your graph. You're going to do some random walk. All right. And then suppose maximum degree in your graph is R. What is maximum degree? How many edges are attached to a particular node. In this example, it's 3. Okay. And in general, you have some bound on your degree. Okay. And then the algorithm goes like this. If you are at a state I, pick one of the neighbors with 1/r probability. Yeah. And then suppose you picked one jth node from the neighbors. You go to that j from your I if stationary pj is bigger than stationary pi. Okay. So you're trying to get a sample from the stationary distribution. You're doing something very intuitive. If in the stationary, this jth node is more probable, let me move that. If not, if it is not more probable, then you still give it a chance to move there. Otherwise, your walk will be very stationary, right? You want it to move around. You say with probability of the ratio, move. With 1 minus this probability, don't do anything. Stay in the node you were at. Okay. And then this just works out using one of those small lemmas I showed you before, which I skipped over quickly. You just plug it in and it shows this algorithm actually goes to stationary distribution. So it gives you a very general way to just run a Markov chain that will simulate your target distribution. All you need is good estimates on how it is going to look like when it is stationary. If you're doing uniform, they're all 1/n, 1/n, 1/n. You know them already. Okay. If not, do some measurements first. Get an idea on your stationary, or do some math. Get an idea on your stationary. Then you can just write down your metropolis testing. It will work out for you. Okay. That's something you will see being used all the time. Since it is very easy and works out in general, why not? Okay. There's a particular case of metropolis hasting called Gibbs sampling. And this Gibbs person was a physicist again. So the people who worked on this stuff turns out to be statistical physics people. They needed to work on it because of their physics, not because of doing computer science. But what they learned is useful for everyone. So Gibbs was thinking about literally kind of particles. Think about them, they're sitting on 2D. I'm right here. I can only go to places where I at least agree on one of my coordinates. Like I'm right here, I either go there, go there, go there, go there. Because with these two guys, I agree on this coordinate. With these two guys, I agree on that coordinate. Okay. So in general, how Gibbs is going to go, I'm at a state. I will go only to places which agrees with my state, every coordinate except just one. And I'll go update that coordinate. That's how the random walk goes. Very simple random walk. Okay. At every step, you're at a state. You are going to go to another state, which only differs in one coordinate. The rest is going to not be updated. And at every step, you're updating a coordinate. Almost feels like coordinate descent technique. Okay. So that's how Gibbs sampling goes. So how do you precisely write it down? You pick a coordinate. You have n coordinates. Pick one of them randomly. Let's say this happens with probability 1/n. And suppose I pick the first coordinate. Now, I can only go for states that has everything the same in second, third, and only changing in the first. And for the first, I have probably several choices. You pick one of them depending on their probability. So what happens is like you pick a coordinate, suppose it was 1, and changing the first coordinate from x1 to y1 is this probability, right? Everything else the same, first one being y1, which is written here. All right. And then now probability of being at that state x and then transitioning to y, if you multiply them together, you get this. It is the same thing as probability of being y, then transitioning to x. Okay. So it's very symmetric. The probability of being at state x and going to y turns out to be exactly the same as probability of being in y, then coming to x. And this symmetry property guarantees that it's going to converge to where you want it to converge. So Gibbs is a much more simple version of the general metropolis hasting, but this is already so useful. You will see this very often. This is usually good enough to simulate so much. And the punchline is either do your metropolis hastings or do your Gibbs, or if you have a more clever idea, do that. Set up your Markov chain, let it run good enough time, and then sample from it. Take that sample, plug that into Monte Carlo, get your Markov chain Monte Carlo. And this is a technique that is used all over computational science and engineering and everywhere, basically. Everybody's doing MCMC. And one little addition we made is like if your vanilla Monte Carlo is not doing great, you can also update it to Hamiltonian Monte Carlo. So you can do basically Hamiltonian Markov chain Monte Carlo. Okay. HCMC, something like that. And I think that's all I need to tell you about this kind of stuff. And that's the end of today.